spray cans, rocket propellant tanks, subsea pipelines, industrial reactors, and this propane tank. They all have one thing in common. Their main purpose is to contain a fluid that's at a higher pressure than the environment. These are all pressure vessels. Pressurized fluids can exert enormous forces on the walls of the vessels that contain them. In this video, we'll explore how engineers apply simple mechanics principles to ensure pressure vessels can safely contain their contents without risk of catastrophic failure. Most pressure vessels are either spherical or cylindrical. One of these shapes handles pressure much better than the other, even though it's less commonly used. We'll get to why that is a bit later on. Let's start by looking at the cylindrical pressure vessel. It contains a fluid at high internal pressure, with the outside of the vessel seeing a lower atmospheric pressure from the surrounding environment. What we're interested in is the difference between these two pressures, the gauge pressure P. The net effect of this gauge pressure is to push outwards on the inside surface of the cylinder, causing stresses to develop in two main directions within the vessel wall. In the hoop direction, around the circumference of the cylinder, from the pressure trying to radially expand the circular cross-section, and in the longitudinal direction, from the pressure pushing against the ends of the vessel and trying to stretch it along its length. Being able to quantify these stresses is the key to safely designing pressure vessels. Let's focus on deriving an expression for the hoop stress first. We can do this by considering an arbitrary section of the vessel, of length L, and cutting it in half to examine the hoop stress within it. Remember that in mechanics, stresses develop in such a way as to maintain equilibrium. The pressure load that acts on the curved inner surface of the cylinder is balanced by the hoop stress in the cylinder walls. The resultant of the internal pressure is a force with a magnitude equal to the pressure multiplied by the projected area over which the pressure acts. This area is the cylinder diameter, d, multiplied by the length, L. The resultant of the hoop stress is a force that has a magnitude equal to the hoop stress, multiplied by the area over which it acts. This area is 2 times the wall thickness, T, multiplied by L. The two force terms must be equal to maintain equilibrium. We can then solve to obtain the famous equation for hoop stress, PD over 2T. A pressure vessel with a diameter of 400 millimeters, for example, that has a wall thickness of 10 millimeters at an internal pressure of 50 bar, which is 5 megapascals, will develop a 100 megapascal hoop stress in its walls. Reducing the pressure, reducing the vessel diameter, or increasing the wall thickness all result in a lower hoop stress. We can derive an equation for the longitudinal stress in a similar way, by taking a circumferential slice of the vessel this time. The important insight here is that the hoop stress is twice as large as the longitudinal stress. This means cylindrical pressure vessels are theoretically more likely to fail by splitting along their length rather than around their circumference, because the material reaches its yield point in the hoop direction long before it does in the longitudinal direction. The next time you're holding a garden hose, another type of pressure vessel, take a close look at the reinforcing fibers within it. Chances are they'll be oriented at exactly 54.7 degrees from the axis of the hose. This carefully selected orientation, called the magic angle, represents the theoretically optimal fiber direction for a scenario where the hoop stress is exactly twice the magnitude of the longitudinal stress. With this angle, the fibers are perfectly aligned to carry the hoop and longitudinal loads in the right proportions. With the hoop stress being the critical stress, It's the PD over 2T equation that's used to calculate the minimum wall thickness required to safely contain an internal pressure P. All we need to do is define an allowable hoop stress, which is often taken to be 80% of the material's yield strength. In welded vessels, an additional factor, the joint efficiency factor E, is often applied to account for the potentially reduced strength at longitudinal welds. It usually has a value between 0.7 and 1. A corrosion allowance is also often added to the calculated minimum thickness to account for material loss over the service life of the vessel. This is a fundamental equation used in the design of pressure vessels. The equation can also be rearranged to calculate the maximum allowable pressure for a given vessel. So what about spherical pressure vessels? The curvature of a spherical vessel is the same in every direction. This means that, at any point in the vessel wall, the in-plane stress is the same in all directions, and there's no distinction between hoop and longitudinal stress like there is in cylindrical pressure vessels. This stress is equal to PD over 4T. This is the huge advantage of spherical pressure vessels. Their shape distributes stress evenly in all directions, resulting in a maximum stress that's half the maximum stress in a cylindrical pressure vessel. In theory, a spherical vessel could be half the thickness of a cylindrical one for the same internal pressure. Despite this, cylindrical vessels are still far more common in industry. The reason is simply because they're a lot less expensive to make. Rolling plate into cylinders and welding on domed end caps is much easier than forming a sphere. Now's probably a good time to mention that we made two big simplifications when deriving the PD over 2T and PD over 4T stress equations. The first is that we treated the hoop stress as a constant value through the thickness of the vessel wall. In reality, it peaks at the inner surface and gets smaller as you move to the outer surface. The vessel wall shown here is thin relative to its diameter, so the reduction in hoop stress is small, and the assumption that hoop stress is constant through the wall thickness is reasonable. For thick walls, though, the variation in hoop stress becomes too large to ignore. The second simplification is that we accounted for stresses in the hoop and longitudinal directions, but we completely neglected any stresses acting in the radial direction. In reality, on the inner surface of the pipe wall, there will be a compressive radial stress equal in magnitude to the internal pressure to balance the normal force applied by the pressurized fluid. On the outer surface, the radial stress has a magnitude equal to the external pressure, which is pretty much zero for a vessel in air. To better understand the significance of the radial stress, take a look at the ratio of the hoop stress to the radial stress at the inner wall surface. If the vessel is thin-walled, meaning it has a large D over T ratio, it's clear the hoop stress will become much larger than the radial stress. In this case, it's acceptable to neglect radial stresses. But if the vessel is thick-walled, the radial stress becomes significant relative to the hoop stress and can't be ignored. It's common to define thin-walled pressure vessels as those with a wall thickness that's less than 5% of the diameter of the vessel. D over T is greater than 20, and a thick-walled pressure vessel for anything thicker than that. The PD over 2T and PD over 4T equations only apply to thin-walled pressure vessels. For thick-walled vessels, the hoop, longitudinal, and radial stresses are given by the slightly more complicated Lemay's equation for thick-walled cylinders. The hoop and radial stresses are functions of the position within the vessel wall. To help you keep track of all these different pressure vessel equations and when to apply them,